Okay, good morning, everyone. I'm Luis da Silva. I'm the Executive Director of the Commonwealth Cyber Initiative, and welcome to all of you to this webinar. Today, we're very happy to have a visitor from the University of Bristol, Professor Reza Nejabati. I've known Reza for many years now. We got to work together on some European projects, for example. He is the Professor of Intelligent Networks at Bristol, where he also has the High Performance Network Group. Reza has a long and distinguished career. He's also an entrepreneur. He founded a startup called Zeta Networks. And today he's going to talk to us about his work on quantum networking. So without further ado, I'll pass the baton to Reza.
Okay. Thank you, Luis. Thank you for inviting and hosting me, and also thanks for allocating some time for me to share my research in my group with you guys. So the presentation I have is the result of research we have done over the last 7 years as a part of the national funding of the UK government program to support quantum technologies. UK program is divided in 4 programs: communication, computing, imaging, and sensing are funded separately by UK government. And my group is leading the quantum networking, quantum communication program in the UK government. And that's where we started. So the first phase of the program, we were focused on security. Now we are not only focused on security, but also focused on quantum computing interconnects as the objective defined by government in UK. So that's where my presentation is also focused on. So first, I will have a very brief introduction on quantum supremacy for the people if they are here and they don't have a quantum background, very quick one. And then I introduce quantum internet. That's the way that in my group we are viewing it. Quantum internet is like a 6G that doesn't have a defined, still to be defined what exactly mean, but at least I put a view on that. And then I focus on quantum networking for security and say why we need a dynamic version of quantum network rather than a point-to-point, which is already a state of the art. And then I say what are the challenges for it and subsystem design. I a little bit focus on the role of the machine learning and AI for managing a quantum network. And then I move on to discuss what does it take for a quantum network to support quantum computing interconnects. I have a few slides which I share with you on the quantum internet and 6G and what is the relevance of it and what the quantum technology can help. And then I conclude my talk. So if you look at the quantum world, very quick introduction. We have a classical bit, which is our two-state, either 1 or 0 is a binary. But quantum bits has a superposition, I mean, of 1 and 0. And I put a Schrödinger cats as an example there just to show the relevance to the quantum. But the 1 and 0, but if you measure the quantum bits, you have a probability of with some probability to measure 1 or 0, depends on how you measure it and when you measure it. So that's where the quantum become interesting. But how you generate it, obviously, is a nuclear spin, electron states. But something is interest for me, especially, is using the photon polarization or photon, because immediately you can imagine if you are in a photon rather than an atomic domain, then it's easy to transfer it. So you can put it in a fiber and transfer it rather than to be confined. And with a nuclear spin and electron state, you have to be confined in the shorter space. You can generate with a heavily attenuated source and pulse it and create a photon that you can basically have a coherent state of and it could basically work at the quantum mechanics domain. So that's one way to generate it, and it's practically possible to generate it. Or commercial version of it is available. Now, become interesting that if you have you go to the quantum mechanics realm of the photon or any quantum bits, then it's impossible to clone it. So it's non-cloning theorem. If you measure it, it collapses the states, as I mentioned, and then you cannot repeat the same thing. So that's become interesting for security. The other thing is entanglement. So if you can create possible to create, we created in my lab, 2 quantum bits are entangled. If you put them in far from each other, I mean, if you measure one of them, the other immediately collapses the same state. So essentially it gives you a mechanism in theory, which what Einstein called the spooky behavior that transfer information more than the speed of the light, if you like, because instantly transfer. So how we created in my lab at this entanglement, we put a very high power laser beam to a special crystal, which is easy to grow. And then that crystal convert high energy photons to two lower energy photons, and that two lower energy photons, some of them are entangled together, which are shown in the intersection of the two cones that are generating the photon in polarization domain. So that's very easy to generate, and the commercial version of it you can buy entanglement photon source now from few companies. Now then teleportation comes. If I have a two entangled photon source B and C, if I collide photon A to B, and then at the same time instantly the combined state of A and B transfer to C. So that's what we call teleportation. So it goes as fast as speed of the light. We can do that in my lab. We have demonstrated, and in the US, Caltech has demonstrated as well. However, the problem is that we can transfer faster than the speed of the light, but we cannot recover the information faster than the speed of the light. Because if I collide A and B, to be able to recover A from C, I have to know what was the state of the B at the time of the collision. So I can measure that, but I have to classically transfer that measurement information. So at C, I have to wait until the information comes from that measurement to be able to recover it. So in theory, I mean, in practice, we go faster than the speed of light, but we cannot recover the information. So still we are observing the Einstein relativity that we cannot go faster than the speed of the light for information transmission. So that's still we are in that state. But this creates a lot of interesting phenomena, which I explained that we can do that. Now, quantum computers, if you have a superposition of a state in qubits, if you have 2 qubits, you have 4 possible basis state, 3 qubits, 8, and so on. So it gives you instantly powerful possibility than classical computer. So first killer application was Shor. Shor developed an algorithm could find, using the quantum computer, a prime factor of integer number in a very finite amount of a time. So that's become baseline for basically breaking RSA security code. And therefore, that say that we have to develop an algorithm which is, so we cannot anymore use AES or anything that is RSA based, that because it's going to be breakable by quantum computer. We need to go a protocol that is secure against quantum computers. There is a famous saying that the Chinas are storing all the things transferred by AES 256, which is common encryption protocol, in a bigger storage for a time that the quantum computer is big enough to decode them. So that's what he says. So quantum computing is good, but we can do certain things like an algorithm, prime factor or factoring is one thing. The other thing, there are biomechanics. That's something that has is that you need a quantum mechanics modeling. For example, interaction of the medicine molecule with the tissue or with the blood and so on, that it goes at the quantum realm. Then you can simulate them with quantum computer very well. You can compute them with quantum computer very well. So that's for drug, for chemistry, but you cannot run it as is not at the moment. If you like, economical or efficient to use a quantum computer for a normal computing process, for a word processing, or what you have as a classical computer. It's good for certain things that you can use them. So it's a quantum computer is not a universal computer. The other thing is become very important is quantum sensing. So if you have a superposition of the quantum state, is very much prone or affected by environmental effects. So you can use this to create a very accurate sensors. At the moment, there are sensors that 10 times better than the classical sensors, and you can have various technology like a quantum mechanical sensor, superconducting sensor, a spin sensor, or cold atom sensors. And also in theory, it's proven if you network the sensor, quantum sensor, practically it's impossible at the moment technology-wise. Quantum sensor, you can get a unbelievable accuracy in your sensing, which is impossible to beat in the classical one. Now, if you look at the application, we have a no cloning property, quantum security, gives us quantum security, superposition of states give us quantum computing, and superposition of a state with the environmental effect give us a quantum sensing, and then entanglement and teleportation, which I explained, give us a quantum networking. So if I want to summarize it in the quantum internet, we say, okay, at the moment there is a quantum sensing technology, quantum computing, and quantum security. What we would like to see in the near future is a quantum cloud computing, quantum data center, and distributed quantum sensing. Meaning that I want to create a, if you like, a Amazon type of the quantum computing facility, which I can scale my quantum computer in a warehouse, and then also I can share it within the users. So that's the ultimate view. And then I can create also an IoT type of mechanism with our quantum sensor. And if I put that that's become a quantum internet, but something I have to do, I have to make this multi-tenant, multi-user, and also I need for that a network. So a quantum network I need for that. That network needs to be dynamic, support entanglement, as I mentioned. And also, it doesn't make a sense I try to build a network nationwide for quantum. I have to make it work with the existing installed fiber or installed satellite system. So that's the challenge that my team works in the quantum network to achieve those capabilities. Let's go on the quantum security. Quantum security at the moment, QKD, everybody heard about it. The QKD is important to note. You use QKD for exchanging the key, not to transmitting information. You exchange the key and use the key to encrypt your data. So the famous protocol is BB84. I mean, what does it mean that if I have Alice and Bob, they want to communicate basically in a secure way, they want to exchange the key first. Alice generates a completely random number for the key, and then also choose a polarization of the photon for each number, either vertical or diagonal, depends on 0 and 1. So you can choose a polarization of the photon just randomly, and then based on the 1 and 0 send the one polarization to Bob as a single photon. So Bob doesn't know what Alice has done, both in terms of the key generation and polarization photon base choosing for his key. So Bob chooses the base to detect the photon. He guesses that I am detecting 45 degree or diagonal degree or horizontal vertical basis. So he chooses the base and detect the photons. And what happens after the key exchange finished? Alice and Bob exchange only the base that they choose the photon, not the key that they detect, only the base of the photon. And for the base that they have a common agreement, they know that their key have detected is correct and the right key. And then nobody has interfered with that, because anybody interfered couldn't not, based on the quantum mechanics, cannot clone it or repeat it. So whatever they haven't detected is either is a wrong base or somebody has listened to it. So that's for sure. So they have missed the information. So that's completely secure. And they use this as a key to extend to encrypt their data and transfer the information. Now, if you look at the state of the art in point-to-point QKD is everywhere around the world. They do the point-to-point QKD, and in US we have a few of them. The most famous one, in my opinion, is the Chicago one around the City Center and Fermi Lab, which is a quantum test space, still point-to-point, but is the only test space support entanglement. So still point-to-point. Which is not very, to me, is just becoming problem now. It's not a network, it's just two single points. And then China has a very big satellite one, is also support the entanglement one, which is most advanced one. But in UK, what we have done, we have a quantum point-to-point link between East Coast and West Coast of the UK. When I say East Coast, West Coast is not a US scale. You have to put it in perspective. It's actually 600 miles. I mean, East Coast to West Coast is 600 miles of the fiber. Goes from Bristol to Cambridge, and that's the point-to-point like anywhere else. However, the interesting thing is in Bristol City we have a dynamic mesh quantum network. In Cambridge we have a dynamically switched network, which is in form of the ring. So that's the advantage compared to the other testbed. Also in Bristol, what we have done, because we have a very strong 5G research activity going on, we have a 5G testbed and we attach it to this testbed. So become a, if you want to do the security at the application level using the 5G with the quantum, we can have a combination of the both. And then in Cambridge, we have a national physics lab and also a major genetics database. So they use that if they want to combine to something to do with quantum communication over the network. So we have this advantage we can do. So I go through that a little bit more detail. So the first thing we want to be doing in my group to focus, okay, if we don't want to install the new fiber, how we using the same fiber to do the quantum information, classical information. If you look at the quantum information, is a single photon. So by definition, it's very weak signal. And then classical information, when you use your internet broadband, is very powerful signal. You pump as much as power you can to go as far as you can with as much as information you want. So that's the problem. So noise generated by powerful signal is becoming very, very difficult for a quantum signal. So that's why most of the places they use the dedicated fiber. So what we did, we tried to see how we can do quantum channel and classical channel in the same fiber. We did very difficult. We have to use to set up manually. We try and error, take 6 months to set up an experiment to do that. So now we said, okay, this is not really practical. We need to come up with an automated mechanism. So what we developed, the machine learning techniques. So we use our test bed, which I showed you earlier, to train a machine learning, various machine learning techniques to see how we can help us to arrange the power of the classical channel and quantum channel parameters based on the fiber condition to achieve the reasonable quality for both classical channel and quantum channel. So we found out that different machine learning techniques for the regression model based on random forest work the best. We are looking at other techniques as well to see how we can do that. So that's a machine learning for coexistence is one of the things that we look. Now, the British Telecom, which is the major operator in UK, is like a Verizon, if you like, here, or AT&T. Also, they are looking to upgrade their fiber infrastructure to the new type of the fiber. The other thing is a multi-core fiber. So they want to install. So we look at how we can achieve the multi-core fiber, also coexistence, classical and quantum channel. So we can have up to 11.2 terabytes if we dedicate one core to quantum. If we share the core with the quantum and classical, 9.8 terabit per second of the classical information going with the quantum channel in the same fiber. So that's something also we have to achieve. The other thing is that also UK is pioneer on the new type of the fibers. So we have a hollow core fiber. Essentially, hollow core fiber is not a silica core, is a vacuum inside. So it's like you're traveling in space. So inside the fiber is completely vacuum. So that gives us a good advantage. So basically, because we don't have a silica, then the classical channel with quantum channel, they don't interfere. They don't have a medium to interfere. So so we can freely launch whatever we want, classical and quantum channel, into the hollow core fiber. And that's something that British Telecom and government are very, very interested, because that's something is manufactured in UK, and they are putting significant funding to install a testbed, a citywide testbed based on hollow core fiber between some government organization and military organization to do that, because freely we can launch whatever condition of classical with whatever power and quantum channel in the same fiber and not affect each other. And the other thing is we use free space. The free space we do with the University of Oxford, because we are expert on the free space communication. How we can do the quantum and classical channeling closely distanced with each other or free space. The reason we do it with the University of Oxford, because University of Oxford are expert on developing the material for quantum computers. So they want to find a way to interface quantum computer together and at a short distance. And free space is one of the way, and we have achieved a good performance of the classical and quantum communication in close distance with each other over a long period of the time, but the distance is 2.5 meters. So it's good if you want to connect things at the rack distance or multiple rack distance. So that's also something that we have done. So we basically create an interface that with classical channel, quantum channel, two quantum channel, and and over 8 classical channel, each of them running a complex modulation format, traveling together in a short frequency space. Now, the other thing is that this is still also we did it with British Telecom. I don't know if you follow news in UK or not. British Telecom is the only operator launched in London a quantum secure service for the customer if they need it. They don't have a customer, but they have done it with JP Morgan, for example, in as a trial, but they don't have a paying customer. They hope that they get a paying customer. But the problem that they found out that big organization like a JP Morgan or a defense contractor that already also using it, they want to use the secure connectivity, which is a fiber coming from fiber, but internally they have a different category of the groups that use that secure connectivity. So it means, for example, one group use, let's say AES 25.6 encryption, but they want to use quantum key for their encryption, that's fine. Another group use Camila encryption, and another group use some proper, especially defense ones, some in-house build encryption techniques that they have developed. So nobody can say, I go to this edge of my organization and use the same thing to go. They want to use all the key, but they want to use different encryption protocol at very high speed rate. So what we have developed using FPGA, a programmable encrypted decryptor, so they can have each port of the encryptor have a different encoding techniques at different rates. So we can achieve up to 190 gigabits per second on a packet by packet basis. We can encrypt the data, and that's being used at the moment. We did as a project with the defense contractor to do that, so they can define per port of the encryptor which encryption protocol they use, and they use quantum key do that. And we can consume quantum key per packet, which is quite big achievement. Usually quantum key at the moment, any key is consumed at millisecond or day time regime. They don't use it, change the key faster than that. But in this, we can do it packet by packet. At the moment, the packet by packet encryption has only military application. But for example, JP Morgan is interested to millisecond change of the keys, for example. Dynamic quantum networking. So now we established what are the problems, possible solutions for coexistence, for the interfacing, but now if you want to create a network, really you need to make it dynamic. So dynamic means that if I have a fiber coming with the information as a quantum classical, I want to be able, like, have a router, I can get the quantum information, go to any output port, and classical information goes any output port independently. So we have developed a switch based on off-the-shelf components, and that try to basically switch the quantum and classical channel independently. We have achieved quite good performance with it, but at the moment we cannot cascade more than 2 switches because simply the loss and other effect on the quantum channel is too heavy, and we lose the quantum channel. Now I am talking with we did it with the people that develop components. We got the component already developed. So now I'm talking with Columbia University to see if they can develop a special type of component, so we can basically replace some of this component to be able to achieve better performance. So the whole idea here, we need a passive switch. We don't need to be fast. Passive switch with low loss and a very, very sharp tunable high Q factor filters. So that's the whole idea. So that's filter and switch is important. The filter at the moment we use a tunable crystal-based filter. For the switch, passive switch, we use mirror, but I believe we use the ring resonator. It's going to get a better performance. That's what I am calling with Columbia University. Now, what we did interestingly on application side, we installed it in our test in Bristol, in the city of the Bristol. All the nodes are equipped with this switch. But what we did interestingly for 5G, so that was with the Facebook and British Telecom, this project. So what we did, we said that, okay, BT said that I want to have my virtualized 5G software. So virtualizing 5G, for the people that don't know roughly, means that piece of the software, piece of the functionality run the software at the edge of the network near the base station. piece of the software run at the data center of the BT or wherever they host their remotely. So they want this piece of the software at the edge communicate with each other and also remote. So the big showstopper for BT, which is not deploying fully this, is security. Because anybody tap to this for whatever reason is a major devastating, major effect for them. They cannot tolerate it. So I said, let's try this with quantum security, and they want to do this dynamic communication between these two sides. So what we did, we created with the Facebook and BT a piece of 4 nodes in different parts of the city, all hosting virtual network function, all the orchestrator of the VNF, virtual network function, all of them are there, plus the physical layer. We put the quantum encryption in each side, and we put the switch in the middle, so BT can decide at any point of the time dynamically which edge of the network to communicate to which other end in a secure way. And then we ended up something that became a showstopper, a very complex software system. So not only has to manage all the virtual function of the 5G, but also manage the security, key management, do the physical layer instruction for communication, and also handle the user. A user comes and I want a communication between multiple points in the secure way. Another user say, I don't want the secure way. One user say, I want a 10 10K key per minute. Once per second, and then this becomes very complex. So we develop the software, we showcase it for 4 nodes, but at the moment the software complexity is being worked out how they can manage it in a BT or integrated Unity system. So that's was showcased with BT. Now let's go. We decided that complexity made us to think about how we can create a more efficient security network. And also a network that it can easily be that network I showed so far, it can be used only for security. But what I want, if I want to have a network, not only can be used for security, but also for computing interconnect. So that's we went for entanglement networking. So entanglement networking, if I have 2 entangled source, if I say to Alice and Bob, so whatever Alice does to that photons, Bob can immediately receive it because they are entangled. And that's very easy to do that. It's not complex. It's very, both price-wise and implementation-wise, very efficient. So that's one way to do that. And we can create a very interesting entanglement relationship between multiple users. So if we have a physical layer, then we can create an entanglement correlation layer on top of that and a entanglement communication layer on top of that. Become very, very interesting. I'll show you why become very interesting. Because look at this, is very simple, look complex, but very simple. Here is our entanglement source in my lab. Is a pump laser with a very cheap crystal. It's easy to grow it, as long as you know chemistry of the crystal. And then what it does, it generates this frequency comb at the bottom. So it's very complex setup as well. So that frequency comb has a very interesting characteristic. Lambda 1 with lambda -1, frequency 1, frequency -1 is entangled. Lambda 2 with lambda -2 is entangled. So I have this huge range of frequency that pairwise are entangled together. So I put this source into this arrangement. So I have a demultiplexer. I put the source. I demultiplex individual frequencies. I put it in a passive switch. So what does it give me allow to do that? I can switch pair of entangled waveline lambda or route them to any 2 endpoints. So I can make an on-demand decision. I want to make A and B have an entanglement relationship together, or A and I have an entanglement relationship together. So it's very easy, and it can do it. It's very efficient. It can work very well. So I can do some clever stuff at the optical layer here, which I don't go through that, but I can do other clever stuff with it as well. But that's become very interesting, and that's we developed the first one, this, and we managed to do very interesting thing with that. So for security, especially with BT, that become very interesting. So if you have an 8 node, instead of multiple source for quantum for 8 source, I put a 1 source. That source I developed is very cost effective as well. So I have 6 people. I want to create an entanglement relationship with that. So you see the Alice, Bob, Chloe, Dave, Faye, and Gopi. They want to have it for security in this case. So they have a different distance. It's a short distance between them and the last phase. So we put it in city of the Bristol with these distances. So what we did, first we tested that if everybody has a source and we are fully connected together, a lot of resources available, what would be the performance of in terms of the quantum communication? But if I use my dynamic switch and partially switch between these two meshes continuously, so I get a full mesh, but in time series, what would be the effect? You see the effect here. So the full mesh is in blue and the partial mesh in the red and purple. You see that the performance in terms of cumulative key that I for security I collected is very much comparable. So I don't get so much penalty, and especially for key is fine. So BT is also going for that. Is become very, very interesting scenario. Now the caveat here is that I need to be able to tune a lot of things here. And if I have an 8 node and 30 entangled wavelength, I end up with 10.6 million scenario to tune. So that's become a difficult one. So what we have done, we developed deep neural network and trained them, and then we are starting using that and become so successful that Chicago and Caltech are using our neural network as well for doing that the configuration of the. So this become very famous. Published very many places. We live demonstrated as well in San Diego last year. So that is being used for entanglement network control, and we use it for security. Caltech using for the teleportation, and Chicago using for the entanglement network as well. So it's becoming very good. So now this shows some great result of this. You see that these are 4 nodes are connected they have an entanglement relationship together. This for security experiment we did it, and the thickness of the line shows the quality of the entanglement link. So better means you have a more entangled photon received and better quality and fidelity and so on. You can parameterize in a different way. Now for different configuration of our switches. Now this shows the predictive. The green shows the predictive, and the red shows our experimental. So the predictive neural network is perfectly matched the experimental results. So that shows how confident we are with our neural network. Now moving on to distributed quantum computing with this 1 qubits to multiple qubits basically. Let's see what's the problem here, what we want to solve. This is the latest project I started in December with UK government funded. Is really, if you want to have a useful quantum computer, it should be really large. So it means you have to achieve more than 1 million qubits. If you look at the one that are in the news, Google 70, 120 qubits, they are working on it, but we are talking about 100. IBM have a roadmap, but the roadmap become very vague after 1,000 qubits. I mean, Quantum, which is a famous one, has a lots of in West Coast, has a lots of funding. Also, the roadmap, immediate roadmap for next few years is a few thousand qubits. But really, if you want to do a molecular chemistry to solve a real problem for real life people, that really you can say I made the impact, you need a 1 million qubit at least, or more than that. They say 20 up to 20 million qubit. So really, how do you want to scale that? There is a famous saying from a very famous person that worked in Google, said that if I want a 1,000 qubit processor, I need a football pitch size cooling system. So that's, you imagine, if you look at Quantum, if you go to their public presentation, the 1,000 qubit they're gonna launch, they're buying the land, big land for the cooling system. So that's because they go at the cryogenic system and Kelvin regime. So that's become a problem. So how do you scale it? One way to go is build a quantum data center. So I have a few qubit processor. Let's go where the Amazon scale, where the Microsoft scale. Link them together to get a quantum computing power rather than monolithically build a super quantum computer. So that's one way to go. It seems that IBM also acknowledging that they are moving to that direction as well. But nevertheless, you need to be able to network to scale. Therefore, we went to that. So there are different technologies to build quantum computers. One is the photonic base is easier, but the one that we work in my project is basically diamond-based quantum computer. Basically, they work in the color center or nitrogen vacancy inside diamond to create the qubits. So if I want to make quantum computer A and B work as a single computer, I have to entangle them together. So I create my entanglement source. I pass it to these two, and this, if they come up with this is a big if as well. If they can interact with the qubit inside the processor, so they can teleport information to these qubits, and they become entangled together, and these two work together. So we are working in this assumption basically. So what we have here, a quantum processor looks like that. It has a processing node based on a diamond or whatever whatever matter you work on it. Then you have a measurement module. You measure your gates, and then the rest is classical. So if you have a data center, what you need to do, you need to also have a network that communicate this thing together between your quantum processor, your classical, as well as quantum level. So we are working in this architecture to connect our quantum processors together. What we are trying to do also take advantage to bring the measurement module out of the processor and bring it and share it within quantum processor and create this entanglement distribution network to connect our quantum processor. So, but now, sorry, I go back to this. Being a physical layer experimentalist, we thought that if there are challenges here to interface and blah, blah, very, very extreme challenges. And even if we manage to do that, we haven't solved the problem because nobody has designed a quantum algorithm can be run distributed. So all the quantum algorithms today are designed for monolithic machines. So we went to the quantum information algorithm, people like design algorithms. So they said, wow, that's if you do the distributed quantum computing become very interesting. Especially I'll go back to this slide because quantum computing people work on a graph. So you see these are H, X, and so on are great. They are statically connected together. So they become very interesting for them if we can dynamically change the graph topology. Because for each subroutine, they can try different arrangement. At the moment, they get a quantum computer, very much everything fixed in terms of the logic gate, and then they need to work on that and design their algorithm. So that's become interesting. So, but nevertheless, we try to get this is the Shor algorithm for a quantum computer. So this is a part of Shor algorithm. You can do the factoring of 21, a small part of it. We divided to run 3 quantum processor and in three different time slots in series. So in parallel and in series. So we try to test, okay, what would be the performance if I run it with the penalty that quantum with the network, entangled network introduced. Since we don't have still all things ready, we did a simulation. So you can see that the blue line, here is the simulation of the detection of the quantum state. The result we expect to see, detect 101 in particular test case we tested. But the blue line is everything run a single quantum computer. The different are in 2 quantum computer or 3 quantum computer with different penalty you get from the network you see here. So you see that still the state is detectable, but if you go too much distribution, the 101 with 110 become indistinguishable. So yeah, if you follow the quantum computing literature, the error is a big problem there. So with this, we started introducing more error. So we have to come up with the error correction system that also consider to that as well. And the whole idea is that our vision is that to create a quantum data center like that. So we have quantum processors. They can be basically organized together or logically connected together like a red, yellow, and green for different applications with different topology, both in the classical and quantum communication. So that's the aim we have in 5-year project that we try to design and implement. We don't have an ambition to implement all of it, but at least to demonstrate part of it. But simulation-wise, we want to implement all of it. Now I move to last part of talk, quantum Internet 6G. I have a meeting with the FCC next week. They invited me to give a talk. I want to test ride this with you guys. You should be done. I mean, that's something. They asked me what quantum internet can do for 6G, also for UK government, because the quantum people, at least in government funding bodies, completely separate from 6G, and they're fighting for money. We as academics try to bring it together to focus on money, funnel money, so we can get a better advantage. Nevertheless, this is something I could think of. It's difficult. It's not easy. So quantum internet has to be secure for sure. And you have to secure against quantum computer. That's no-brainer. So something that needs to advocate, UK government advocate, we have to go post-quantum cryptography. Fine. Although people break it in the Starbucks, which you have seen in the news, but there are still good algorithms there, you can run it. But those good algorithms, if you look at it, the epileptic form and so on, are computationally heavy, very, very heavy. So if you means that if you want to run at your base station encryption, you have to have substantial computation power to run your post-quantum cryptography. So if you want to do that, you consume energy. If you have enough energy, fine. But if you don't, if you want to go to zero net and green and all sorts of things that governments are advocating, then that's not a really wise way to go. So quantum security is good one. It's a photonic base. Is cheap nowadays, commercially available, doesn't consume energy. It works in the room temperature or environmental temperature. So to me, it's very energy efficient. I don't say I don't disregard post-quantum cryptography, good cryptography in terms of the resistance, but they can certainly compete with quantum security, but in terms of energy, they cannot. So that's one thing to think about. For quantum computing, a lot of things, especially on spectrum mapping, has a quantum mechanics nature or a stochastic nature of the. You can model in quantum mechanics the stochastic nature of it. People have done it, especially in MIT. I work with one person does that. Then quantum machine learning become important. Quantum machine learning is a buzzword. You really you have to get it with a big pinch of salt, but especially it's good for solving those type of problems. So spectrum planning does become something else. And also, I guess you want like the way Amazon and advocating providing quantum computing as a service. You want your 6G network to provide quantum computing as a service, not for everybody, for whoever needs it. So that's something the quantum computing plays in 6G. Something is, I think, is the most important one, is the ultra accurate distributed sensing or sensing. Quantum computing, especially sensors, to me, immediate application, very immediate, you can do it, start doing it today, is a spectrum sensing. So you can do a very, very high resolution spectrum sensing with the diamond-based quantum sensors at the range of from Wi-Fi frequency get to the all spectrum of the 5G. You can do that with a very high accurate range. And it's possible to do that. It's not a science fiction. People have shown it. So that's, to me, not for the self-free operation, but I can see for self-free operation can be done. Then quantum-based atomic clocks also for high accuracy synchronization. I am not sure what I know. Have a good awareness of what is 5G synchronization requirements, but I am not sure what will be 6G. I have seen some numbers, but there are various things. But seems to me atomic clock also is very good, and it's possible also to implement it. Then there are various localization, accurate localization possibility. I have seen some publication from Virginia Tech on location-based localization based on quantum devices. That's also something achieve accuracy for 6G. Now, to conclude my talk, I would say that dynamic quantum network is a fundamental for realizing quantum internet. There is a realistic prospect. It's not science fiction. You can build it at the moment. We have shown it. You can build it to support large number of the nodes. You cannot go large distances. So I say larger scale, you can do it with a large number of nodes, but you cannot go large distances. That's a problem. Machine learning seems to be essential part to manage it if you want to really deploy it in the application. The problem to address going long distance, loss and cascadability like quantum repeaters and so on. Also, in terms of the entanglement, the fidelity or efficiency of our entanglement is very difficult to get the accuracy that we want for. Is good for security, is not good enough for quantum computing interconnect. For a quantum computing interconnect, depends on what you do, but you need more than 95% fidelity. At the moment in the lab, we are pushing it to achieve that very, very controlled environment. So it practically is difficult to achieve. So that's something that we need to work. So these are the teams that I presented the work, collaborated with me on this. Okay, thank you very much. So this is a multidisciplinary. We have algorithmic people here. We have a physicist people. John Wright is a very famous physicist as well here, helping us so on. So yes, thank you.
Thank you very much, Reza.
Is there a question?
We'll open up for questions. You can use the chat box, and I think there are comments or a question at the moment. Oh, can we keep the slides as a reference?
Yes, I can share it with you. Yes.
Okay. So we can.
I can share. I send it to Susie.
Excellent. Perfect. Any other questions?
I hope as it was useful. It was not out of context.
No, it's not out of context at all. It's very much in in the mainstream of what we've been talking about and
I think
investing in. We have a couple of
Now we get
questions.
some questions. Yeah.
When we think about distributed sensing, we also need to think about sensor fusion. Are there any challenges in quantum sensor fusion that we need to address?
sensor fusion, at least the one I understand, unless you have to tell me, is information fusion of the sensor. Is that correct? When you have a distributed sensing, or I don't.
I think that's what.
Yes. So yes, when you do the these are. I mean, if you look at the quantum sensor, one is the creating quantum effect that are affected by environmental condition. That's one challenge. The other is the measurements. And the measurement at the moment, there are published theory that distributed sensing, there are methods which already published. I am happy to share the references that how you can combine the measurement from different localized sensor to come with the unified measurement from your distributed sensor. Yes, there are work needs to be done, and it's a serious information theory works which has already been done. The foundation of theory is already there for distributed. This is called distributed sensor measurements. Yes.
Then Joan's asking, how do you think 6G can leverage quantum communications?
I think I said that one is for security for sure. For me, for communication, then access to quantum computer as a service. That's the second one. That's the two I can see would be yes. The rest of it is quantum sensing as an application of system.
Yeah, because in fact you mentioned, I get to jump in, so
Sure.
must be present to win. Like with key distribution and all that, would it still be classical to a handset or actual QKD all the way down to the user devices?
There is a commercial reason and other things, but for example, I work with a group that does the Wi-Fi. And what they do on the iPhones, they are creating a Wi-Fi transceiver that uses a camera, the light here to do Wi-Fi, and they want to implement the quantum security QKD on that. So that's come onto the device. But that's for the iPhone that supposed to go for iPhone that goes to officials. For example, if somebody wants to go to a meeting and want to have a secure communication, they use it. Not for the public to produce it. So that sort of thing I am seeing. But at the moment, you have to see where is the security bottleneck in your organization. If it's the edge of the network in your government building or your institute, that's become where, or if it's a device. But especially on Wi-Fi, because the optics and we can do quantum quite interestingly there, it's become important because you can have a sitting around here, and then you can have a individual quantum communication with different people around the table. So that's something that, or also free space quantum communication for drones, for short range drones. So if drones, that's the work we do with the Elbait is a defense company. So that's for short range. They do that as well. But I haven't seen anybody claiming for consumer.
Right.
Ari, can you scroll down? There may be another question. I'd like to see this paper. So Marcus, I think, is interested.
I will share. Marco, if you send me an email, I have it in my laptop. I'll share it.
Because it sounds like a bunch of papers.
Yeah, but I think Marcus may be interested in the information theory aspects of the.
Yeah, there is a proof information theory that distributed quantum how it works. Well, the problem is that distributed quantum, the sensor is there, measurement is there, theory is there, but the interface to network is not there. It's very difficult to make it, especially for quantum sensor. I mean, that's I would say is 7 to 8 years away. The other.
I have a non-technical question because when we started working together, your focus was more optical networks.
Yeah.
What was your trajectory into quantum information science?
What happened? Why I moved, because I work on optical and application of optical. The Quantum Hub program started in UK. After 1 year and a half, they run by all physics people, and they have a quantum communication program. So they said that they didn't get anywhere. So there was a call for the people that they have a classical communication background to come, and they joined the program. So I joined that program, and then I ended up leading the program. So that's where my work started, and then I built because of the funding that they give me, I built a research group and I started to work on the quantum communication. My quantum information theory is at the moment is only focused on the how to distribute quantum computing. Recently, algorithms, how to separate them in a distributed way, and the other, and what would be how you can optimize, because when you distribute, you have to sacrifice some gates and logics, and how you model that in linear algebra and so on to see what you do in physical and make sense. On the security proof. On what we do, because what I show you on the slide about how the security work and the polarization is a single photon. Realistically, single photon we cannot transmit. What we transmit, we coexist, means that we transmit few photons. If I transmit few photons, you as a if eavesdropper or an adversary attacker can grab one of those photons and try to detect if we have a very good receiver, let's say. If that's how I can security proof that the coexist. We do also amplitude modulation, so on that sort of also work. Because on practice, how you can really model this thing. So I am not information theorist, but I do for what I do use information theory to prove this.
Oh, more. Question from Jeff. For those who have classical training in communication and networking, how do you suggest those researchers spin up and position themselves? I guess there's a play on words.
I know. I was thinking that too. Get their orientation, get their face together.
To spin into the quantum information science scene.
I say you my experience. I don't know who is in the call. Well, I have to say, I say in UK. I mean,
there are clearly a lot more people than we see.
So the problem with quantum domain is dominated with the physics. We need a physical scientist, but for applying it to application, really need to move on. I mean, I think we need to start in the quantum joint. What UK government did, because of we pushed quite a lot, few people like myself. You need to advocate with the NSF to do the joint ICT quantum calls. So bring the people, they force one PI from the classical ICT, one PI. So to come up with the application and use cases that needs the quantum communication. But for example, the 5G one, the only person who did it was my group, because we had the right, I was lucky or was in the right point to be entered to this quantum program of UK. And then I had a 5G awareness and neural networking. I say, hey guys, we need that. And BD said, oh, we have a use case for it. Let's go and do it. And then Facebook jumped in and said, oh, we have devices for hosting and so on. We want to see how we behave. So that's how we are. So guys, you know the classical, what are the problems? So then if you basically try to work with the quantum people to see how you, I found the quantum physics, they have a difficulty to map their solution to problem. But the ICT, classical ICT engineer are very good to solving the problems. So if we see what solution they are there, I think we can come up with the problem, which I show you a few of them, how I came up with a unique angle for myself to solve those problems from looking. So nobody was thinking before my group to use machine learning for quantum solving problem, quantum classical. Now machine learning, for example, used by few universities in US, to the machine learning they use, they have adopted to use to control the polarization, which is nothing for calculation, but they use the same effect to use it. So we can help them a lot. I mean, that's what I can say. I hope I answered your question, but it's something that you can do personally, but something also you need to advocate with the government agencies.
Reza, thank you so much. This was great. Thank you to everyone who attended in cyberspace. I can't.
There are clearly a lot more people than those pictures.
So that's fantastic. So thanks for the visit. Reza is going to spend the afternoon with us as well. So there's going to be a lot more discussions with faculty and CCI and elsewhere. All right. Thanks, everyone.
Thank you.